Hey everyone, and welcome to This Explainer. I'm your host, and as a technical adhesive expert here at Sanligao VN, I spend my days obsessing over the exact science behind how things stick together on an industrial scale. Today, we're unpacking a massive, high-stakes trade-off that manufacturing engineers face every single day on the assembly line. The big question is, do you prioritize slashing your cycle time down to mere seconds, or do you absolutely require the deep, guaranteed structural integrity of a sustained heat process? We're going to strip away all the marketing fluff today. We are looking strictly at the objective mechanisms, the hard specs, and the safety data of UV curing versus thermal curing thermosets. So, let's just dive right in.
So, which curing method actually wins on the line? Well, to answer that, we have to look at the physical realities. Actually, I have a great way to show you this. I've got two pieces of opaque plastic right here. I'm going to put some UV glue right between them, and now I'm hitting it with a high-intensity UV flashlight. Okay, now when I pull them apart, look at that. The center is still completely liquid. It's a gooey mess. And this right here is the absolute core limitation you have to wrap your head around before you even think about designing your line.
Okay, moving right along to Section 1, Mechanisms of Curing and Their Chemical Triggers.
To really optimize throughput, we've got to understand the objective chemistry of how these work at a molecular level, right? Notice the stark contrast in the physical triggers we're looking at here. Over on the left, UV curing relies entirely on what are called photoinitiators. According to manufacturers like Dymax, these little guys are highly calibrated to react instantly to very specific UVA wavelengths, typically right between 320 and 395 nanometers. It is strictly a line-of-sight reaction. On the right, thermal curing is a whole different beast. It requires heat-activated exothermic polymerization. Basically, you need sustained heat, often baking between 130 to 150 degrees Celsius, to force this massive, uniform chemical cross-linking throughout the entire adhesive bead.
And this brings us right back to the messy phenomenon I showed you a minute ago. It's called shadow curing. If that specific UV wavelength cannot physically penetrate an opaque substrate, or if it can't reach inside some complex internal three-dimensional cavity, well, the photoinitiators never trigger. The adhesive literally stays liquid. It's a severe geometric limitation for UV systems. Thermal adhesives, though, they do not care about shadows. Heat permeates where light simply cannot, ensuring you get a uniform crosslink regardless of how crazy complex your assembly is.
All right, Section 2, the spec showdown. Let's see how these mechanisms actually translate to throughput on the factory floor.
Looking at the data, the most glaring difference is typical cure time. UV needs just half a second to maybe 5 seconds to fixture. I mean, blink and you'll miss it. Thermal, you're looking at anywhere from 5 to 60 minutes. But you can't just look at time, look at the equipment footprint. A UV lamp takes up maybe 1 to 2 meters of line space. A batch convection oven, on the other hand, is going to dominate 3 to 15 meters of your valuable floor real estate. The big trade-off, as we see here, is that UV generally demands transparent substrates, whereas thermal gives you totally unrestricted depth of cure on those opaque, complex geometries.
Now, before you completely dismiss thermal as being way too slow, you have to look at modern advancements. For instance, if we pull the spec sheet for Zymet's X6825LV underfill encapsulant, we actually see a highly efficient thermal cycle time of just 4 minutes at 150 degrees Celsius. And for those 4 minutes of baking, you yield some incredible structural metrics, a glass transition temperature, or TG, of 120 degrees Celsius, and a coefficient of thermal expansion of 31 parts per million per degree Celsius. That right there is guaranteed rock-solid deep cure stability. But then, you contrast that structural heat process with the sheer, blinding speed of a UV solution like the Dymax 3025. Evaluating their technical data sheet, it shows that when exposed to an intensity of 200 milliwatts per square centimeter in the UVA range, the fixture time is literally less than 1 second. Less than a second! If you are manufacturing high-volume, transparent assemblies, the throughput capabilities of UV are completely unmatched by absolutely any thermal oven on the market. It's a total game changer for the right application.
Moving on to Section 3, EHS and Safety Check. Because speed and strength are great, but we absolutely cannot ignore worker safety and health realities.
Pulling straight from the safety data sheets, we see a huge difference. UV adhesives are generally 100% solids. That means zero VOC emissions, which is fantastic. However, they do contain specific irritants like acrylic acid, that's CAS number 79-10-7, and it carries a very tight 2 part per million threshold limit value. To put that into perspective, 2 ppm is a microscopic margin for error, mandating strict UVI and skin protection. Conversely, thermal epoxies involve heated vapors and epichlorohydrin polymers, CAS 9003-365.
Because you are physically baking these chemicals, they absolutely mandate dedicated local exhaust ventilation and specialized respirators. You do not want your team breathing that in. Okay, Section 4. Top pros and cons. We've covered a massive amount of technical data, so let's distill this down into a quick summary of your trade-offs.
Here is your rapid-fire summary. For UV curing, your top pros are those incredible sub-5-second cycle times and a tiny equipment footprint that saves precious factory floor space. The cons? Severe shadow cure limitations, and it absolutely restricts you to transparent or highly specific substrates. Now for thermal curing, the pros are undeniable. You get a guaranteed, deep structural cure that works flawlessly on complex, 3D, opaque parts. The cons, though, are the unavoidable bottleneck of those 5 to 60-minute cycle times, plus the massive footprint and energy cost of running those huge industrial ovens.
Which brings us to Section 5, the final recommendation. How do you actually choose?
Based on my 10 years of evaluating adhesives, here is your definitive mandate. Switch to UV if your absolute priority is slashing assembly line time down to seconds and your parts are definitively transparent. Stick to thermal if you are manufacturing highly structural assemblies with complex, opaque substrates where a shadow cure failure would be catastrophic. You've got to look at your geometry, look at your throughput targets, and just let the data make the decision for you. Thanks for joining me on this explainer today. I'll leave you with this final thought. As automated assembly lines get faster and product geometries get smaller and smaller, will the industry finally find a way to make light bend through solid plastic? Or are we just destined to keep baking our electronics in ovens forever? Something to think about. See you next time.